In this tutorial, we're going to be talking about electron affinity. So as the name specifies, affinity is the affection of an atom toward an incoming electron, and it's usually measured by the energy released. So if you add an electron to a gaseous atom, there is going to be a release in energy. If an atom releases more energy after getting the electrons in, it's said to have higher electron affinity. If it releases less energy, then it's said to have lower electron affinity. Now, when I'm writing this equation in, I would have, let's suppose I got an element here, E, and I'm adding an electron to it. When I add an electron to it, it becomes E1 minus, okay? And it's going to have some electron affinity onto it, which is actually going to be in a negative number, which means it's an exothermic reaction, which makes sense because remember the exothermic processes are the one that releases energy. So if you release more energy, it's a good thing for an atom to getting an electron. Now, the question you really want to ask yourself when you're trying to determine the electron affinities is when will it be easier to add an electron? And we have talked about ionization energies, and the ionization energies more or less is a very regular trend in the periodic table when we are going from left to right and top to bottom. But when it comes to electron affinity, it does have a lot of irregularities. However, I'm going to look at it in a big picture here and talk about just the general trend of electron affinities. Now, if an atom is smaller, so if I take two examples, let's say I have this element A here, or atom A here, and I got an atom B here, and those are the perimeters, so atom A is actually bigger in size than the atom B here, and I'm adding an electron to it. So if I'm adding an electron to an atom A and adding an electron to an atom B, in which particular case it's going to be easier to add an electron? Well, turns out any added electron must be pulled in by the nucleus because that's what's got the positive charge, and it must have some attractive force coming from the nucleus to an added extra electron. If the nucleus is very far away from the valence shell where the electron is going to be added, it's not going to be that easy to keep that electron there as opposed to having a smaller element, and it's going to be easier to add an electron to the valence shell. So another way of saying, if you add an electron to a relatively smaller element, it's going to have a higher affinity as opposed to adding an electron to a bigger element, which is going to have a lower affinity. And obviously there are going to be a lot of exceptions, and I'll talk about some of those in there. So we say higher affinity means more negative number in terms of electron affinity because it's an exothermic reaction. So if we say the electron affinity is actually increasing, it just means it's becoming more negative and negative. Okay, so when you're going from along the period in the main group elements, we know the atomic size decreases. So since the atomic size is decreasing, it's going to be easier to add an electron, so your electron affinity increases. All right, and another way of saying it just becomes more negative. Okay. On the other hand, when we're looking at down the group, when we're looking at the atomic size is increasing when you go down the group from top to bottom, and if the atomic size is increasing, your electron affinity actually decreases. And what that really means, it becomes less negative, or you will see even sometime it becomes positive. or becomes more positive, because you really don't want it to be positive, because in that case it would be actually requiring energy. You don't want to be requiring energy to add an electron. Okay, so when I'm comparing the metals versus nonmetals in terms of the electron affinities, we know nonmetals, they like to gain electrons. Okay, and metals, we know they like to lose electron. Okay, so since nonmetals, they like to gain electrons, they usually have high electron affinity. And metals, on the other hand, will have low electron affinity. And that trend is usually safe enough to assume all the time that metals, when you're comparing a metal and a nonmetal, nonmetal would have a higher electron affinity than a metal. Obviously, except the noble gases. That's the second exception I want to talk about here. When it comes to noble gases, it's just a nightmare to add an electron, because noble gases already have a stable electronic configuration. All right, so if they already have a stable electronic configuration, why bother adding an electron and disturbing that stable electronic configuration? So noble gases usually have very high positive values for electron affinities. Okay, sometimes even higher than the non-metal, higher than the metals. So when you're comparing between the metals and non-metals, that only applies up to group 7A, which is the halogens. So when you're looking at noble gases and comparing the electron affinities with the metals, it doesn't really work very straightforward. You may have to look at the actual numbers. But if you're just comparing the metals with just the regular non-metals up to group 7A, usually non-metal is going to win in terms of the electron affinity. Okay, some other exceptions let's focus on here. So I have one exception here, but when you're going from group 5A to 6A, and we saw that exception in case of ionization energy as well. So nitrogen has a positive electron affinity, which means it doesn't really want to have an electron added onto its shell, as opposed to oxygen has a negative electron affinity, which means it's higher electron affinity. And then when we be looking at carbon here, carbon also has a negative electron affinity. So when you're moving from across these three elements here, I should expect a regular increase in the electron affinity, or another way of saying these numbers should have become more negative and negative as we move along. But nitrogen turns out to be a positive number, which means it has a low electron affinity. Carbon have a higher electron affinity. So this is one of the exceptions here, where even though nitrogen is further on to the right than the carbon, nitrogen still have low electron affinity than the carbon. Okay. In addition to that, the other one I want to focus on is the group 1A and the group 2A. So as you're moving in the same group, we expected that electron affinity should become more negative. So beryllium should have a more negative number for the electron affinity than the lithium. However, that's really not the case, and that's because beryllium has a stable electronic configuration relatively to the lithium, because beryllium is going to have a 2s2 at its valence shell, and lithium is going to have 2s1. So you can still add one electron to make a 2s2 in case of lithium, but in case of beryllium, it's already fully filled for the 2s. So that's why it does not like to have an extra electron, because it will break in the stable electronic configuration. So beryllium has low electron affinity than the lithium. So like I said before, there are a lot of exceptions when you're looking at electron affinity. The trend of electron affinity is not as clean as you would see in case of ionization energies. However, you still want to keep in mind the overall trend of electron affinities for the main group elements and know some of these exceptions like noble gases, group 5A, groups 4, 5, and 6A, how it's behaving when you go from carbon to the oxygen, and obviously between 1 and 2. Okay, let's look at this example here. We're trying to arrange the electron affinities for the calcium, chlorine, and aluminum. So when I'm change the color there, so when I'm looking at calcium is going to be right there, and then when I'm looking at aluminum, it's going to be right there, and when I'm looking at chlorine, it's going to be right there. Okay, so as you go down, the electron affinity obviously decreases, and when I'm comparing just generally in terms of between the aluminum and chlorine, chlorine should have higher electron affinity because it's more onto the right side, and they are obviously in the same group, same period rather. So chlorine is going to have the highest electron affinity, and then aluminum is going to have lower electron affinity than the chlorine. And then between aluminum and calcium, it may be a little bit of a war who's going to have a lower electron affinity, but it turns out calcium being a stable electronic configuration, because remember what we said about group 2A element, they really don't want to have any electron added onto them because it will break their stable electronic configuration that they already have. So as a result, calcium would have a lower electron affinity than the aluminum. Okay, so then let's focus on this one right there. So we got oxygen. Let me change the color there. So we got oxygen, nitrogen, sodium, and argon. So argon is right there. Sodium is going to be right there. Nitrogen is right there. And oxygen is right there. Okay, so obviously we said metals has low electron affinity than the non-metals, okay, except the noble gases. Noble gases is very, very low electron affinity. Nitrogen and oxygen are more onto the right side than the nitrogen, so oxygen will have higher electron affinity. So I can easily say oxygen is going to have a higher electron affinity than the nitrogen, okay, and then between argon and sodium, argon is going to have less electron affinity because it's a noble gases. So argon is going to be way right here, and then sodium is going to be higher electron affinity, and then it's going to have nitrogen is going to have higher electron affinity than the sodium, and obviously the oxygen is going to be the biggest in this particular case. Okay, so that's how we're going to be looking at electron affinities. Let's focus on metallic character. So sometimes they ask you questions like, okay, which particular metal is going to be more metallic in character? And if, as the name specify here, the character of the metals is being shiny, they are good conductors of heat and electricity. That's why you use copper wires in the household. For the electricity purposes. They are malleable, which means you can kind of beat them down to the sheets. They are ductile, you can easily cut them into the wires. But those are the physical properties of the metals. But let's focus more or less on the chemical properties of the metals. Chemically, metals, they like to lose electrons. So if something is more likely to lose an electron, they should have low affinity for the incoming electron, and they should also have a low ionization energy. So having a low ionization energy means it can easily lose an electron. So based on these two principles, metals should have low electron affinity and low ionization energy. We can clearly say when you go from along the period from left to right, your metallic character decreases. And it would probably make sense because, onto the left side of the periodic table we have a lot of metals, but as you move on to the right side we are putting a lot of non-metals in there. But when you're going down the group, your metallic character actually increases. And why is that? That's because as you go down the group, your ionization energy decreases. The metals, they can easily lose the electrons when they're way down in the group than being on the top. And same story, their electron affinity is also low when they're down on the group. So sometimes they may just ask you, okay, I got two metals here. One is potassium and the other one is francium, who's going to be more metallic in nature. Well, francium is way down in the first group than the potassium, so francium is going to have low ionization energy. It's going to be very easy to lose an electron when it comes to the francium than the potassium. So francium would indeed be more metallic in character. If I pick maybe Suppose if I pick something onto the right side of the periodic table, suppose you got silicon and maybe sodium. So as you move to the right along the period, your metallic character decreases. And as a result, sodium is going to be more metallic in nature because it's onto the left side of the periodic table. All right, so that's how you're going to be looking at the metallic character.